Uh, Welcome back, students, to our second section or lecture of economics of innovation. We ended last week with this overview actually, and what I noticed is I was going on talking without going to these slides. So what I pretty much did in the very last minutes of the last Tuesday's lecture was giving you this overview of the course. I just want to jump right into the models of imperfect competition right now, showing you the benchmark or workhorse models we are going to use in order to analyze research and development behavior and activities of firm and innovative behavior. And then we will move on to look into what is called here the basic model, which is actually the Arrow model from 1962. Okay, so hopefully the stream works, and we are going to move on to these models of imperfect competition. Of course, the most pure model of imperfect competition is a pure monopoly, where we have a single supplier not facing any threat of entry. So entry is, for instance, legally or for some other reason banned. This monopolist faces a negatively sloped demand curve, and I told you already, no potential market entry. I just want to present some notation. X, or later on also Q, will denote the quantity of the good, but for the minute this is X. We have a cost function, C of X, which denotes the cost you have if you produce output quantity X. You have an inverse demand function, which is negatively sloped. The capital pi here, the Greek letter, denotes the profit of the company. And we assume that marginal costs are non-negative, so positive or zero, if you think of software, for instance, and that demand is negatively inclined. So if you want to sell more, you have to reduce the prices. Okay, that's for the start. What does a monopolist do? We assume that a monopolist maximizes profits, and then it's straightforward. It maximizes profit pi, which is nothing else than revenue minus cost. Revenue is price times quantity, or as it put is here, quantity times price. Here I put revenue in terms revenue in terms or price as a function of quantity. We also could just do the other way around, quantity as a function of prices, and take price as a decision variable, but here we maximize by choosing X. It doesn't matter for the monopolist, because if he chooses a quantity, the monopolist gets, the monopolist directly gets the price, the respective price from the demand curve. The first order condition is then just derived by taking the first derivative of the profit function with respect to X. Here what we have then, of course, is marginal revenue. Price plus something is equal to marginal cost. And I learned that I could also use the laser pointer. So the big difference to perfect competition is here that you have this additional part xp prime of x, namely marginal revenue is less than the price, because if the monopolist wants to sell more units, it has to reduce the price, and as p prime, the derivative for the slope of the demand curve is negative. This is negative, and so if you want to sell one more unit, you get the price for this unit, but you have to reduce the price of all inframarginal units which you would have sold anyway. Of course, we can slightly rearrange that by using the price elasticity of demand, which is simply defined as it is written here, dx over dp, that's the derivative of the demand function, times p over x, which is nothing else than, if we would put it differently, dx over x over dp over dp over p, which is nothing else than in a denominator the percentage change in price, and in the numerator the percentage change in quantity. So by how much quantity, by how many percent quantity changes if price changes by a certain percentage. And of course we always have the minus here because we do that in absolute terms. Oh, you can hardly see that, so I do it up here again. In absolute terms, because we know always that if we increase the price, the demand goes down, or demanded quantity goes down. Now we might rearrange that, just play around here, factor out P, so that you get P is 1 plus X, and write the X or write P prime as dp over dx, and you see immediately, oops, somehow I get problems here. Somehow you see immediately how you can come up with the so-called Amoroso-Robinson relation. This will be helpful to derive, for instance, the optimal price. If you go to, oops, if you go to where is we? To assignment 1. Here you have a so-called isoelastic demand curve, and what you see is if you have such an isoelastic demand curve, it's rather helpful to use the Amoroso-Robinson relation to calculate that, because you immediately know the markup. Now, this is now the first order condition put in terms of the Amoroso-Robinson relation. It just tells you, you could just put this expression on the other side, then it would tell you by how much higher or how much above the marginal cost prices. So if epsilon is 2, this would be 1/2. So you would get that price times 1/2 is marginal cost. So put the 1/2 on the other side. So you see that the price is 2 times marginal cost. So if you have marginal cost of 100, the price would be 200. Of course, epsilon greater than 1 must hold. Otherwise, you run into trouble because you would get negative prices. Of course, that doesn't make sense. I discussed that a lot in economics of regulation. I don't want to spend a lot of time on this issue here. The point is that in this case, if you have inelastic demand, monopolists just would sell as little as possible at an extremely high price. We might, or Max might discuss that with you if you have, for instance, an isoelastic demand function with an epsilon of 1, you would see that the monopolist would just sell 1 unit at the total revenue of the market, which is always constant. Yeah, you might also put that in terms of the learner index. This is just rearranging this equation here. And the learner index just is a measure of market power. In the numerator, you have price minus operating costs. So this is in a sense the operating margin or the operating profit divided by P. So it's the operating margin. So again, our example, suppose the demand elasticity is 2. So you would get that half of the price is profit in a sense. Okay. Yeah, I think that's supposed to be it. What I want to do as a start. We will discuss that in much more detail later. Here's just a standard kind of diagram you use here. GE means Grenzerlös. This is marginal revenue, which has twice the slope of the demand curve here. Here you have X a quantity on the X-axis and P the price on the Y-axis. At the intersection of marginal revenue and marginal cost, you can get down to the X-axis and you get the optimal quantity, the monopoly quantity, moving up to the demand curve, and across to the price axis, you get the marginal price. You see here, what is this? This is producer surplus. This will be a very important measure in our economics of innovation course, because suppose you're an innovator producing a product innovation, bringing a new product to the market, and this new product has marginal cost like this, and you face this inverse demand function. You exactly know what the operating profit will be. And of course, you will only, and this is this rectangle here, the producer surplus, and of course, you will only be willing to introduce this product innovation if product development costs, which are fixed costs, if product development costs are smaller than this year. And we will get back to this kind of arguments in once we discuss the arrow model. Okay, that's about it for the monopoly, and that's pretty much what I usually do already in my Micro 1 course, in the principles course for the freshmen. Now we look to our first workhorse model, which we very often use, a Bertrand competition, namely Bertrand competition among homogeneous good producers who have identical and constant average and marginal cost. So flat, constant marginal cost, like in our previous case here. So we have this kind of flat marginal cost curve, which I highlight. I could better actually with the highlight marker, which I have here. Okay, assume that these two firms in our duopoly have this kind of marginal costs and no fixed costs. So this would also be the average cost. Now, and these are greater than 0, and they are homogeneous good producers. And now the important insight of Joseph Valrat in something published in something like 1880s or something like that was, if you have a standard demand function with negatively sloped demand, you get a really weird kind of equilibrium, namely price equal marginal cost, which is a unique equilibrium. So the B stands here for Bertrand. This is a so-called Bertrand paradox. You have cutthroat competition. Just think of Schiffenberger Tal. There are two gas stations there, an Aral and a Chet, or I think it's a Esso. Anyway, and the point is, if they were located just next to each other, and everyone assumes that the gasoline you get there is really homogeneous, no differences, and you don't have any fleet cards or any ADAC bonuses or something like that, of course, the price would go down to a marginal cost. Why? Okay, suppose they have marginal costs of €1. Someone charges one station charges a price of 130. Then the other station would have an incentive to undercut and charge 129, and every consumer would go there to fill his gas tank. And of course, that goes on. The other station would then really undercut and would charge 128 and so on. And the only equilibrium you end up with is then price equal marginal cost, which I assume to be €1, which is surprisingly realistic right now. Okay, so that's a Bertrand paradox. Of course, this is a very, very special kind of result, and it depends on a few assumptions, in particular on unlimited capacities. So in terms of say, cement, it would hardly work because you have cement production capacities which are limited. The Bertrand paradox requires that in equilibrium, if you have a duopoly, each firm will actually have about half of the markets in terms of demand. But in order for this undercutting process to work, it has to have the full market capacity. So it has to have 100% excess capacities. If capacities matter, we get into Kuno model, and this is what I will present to you later. Again, we assume these are homogeneous goods. If these were two bakeries located 1 kilometer from each other, of course they can charge a different price for their croissants probably, because if you live next to one bakery, you hardly would like to pay 10 or 20 cents more than walking for a kilometer or something like that. Okay, and we will discuss product differentiation later on as well. Product differentiation might also be part of an innovation strategy. You just produce a differentiated products. And it also assumes that you have a one-shot game where you do not have any kind of collusion. That's a topic we discuss at some length really in the undergraduate IO course in competition policy. And finally, it assumes that you have identical constant and average and marginal cost. So we have in I/O, we abandon this assumption of unlimited capacity. With I/O, I mean the industrial organization course I'm going to teach in the winter again, and I taught in the last winter. We have a two-stage capacity game where we look into the same situation. I already mentioned differentiated products as a departure from homogeneous goods. And repeated and super games, we wouldn't do that, but with a super game, so a game which is infinitely many times repeated. Is it possible to say infinitely many times? Anyway, okay. So it's permanently repeated, and then you would have also collusive equilibria where these two companies, these duopolists, tacitly collude on a monopoly solution, for instance. But what we want to do is now, and this is very relevant, of course, in terms of economics of innovation, we want to abandon this assumption of identical cost. Okay, because the point of say, for instance, introducing a process innovation is that you just reduce the cost below the previous level. And if you start out with having the same cost as your rival to begin with, what happens if you, as company one, or if you are able to reduce your costs below the level of firm two? Okay, and now how does the equilibrium look like? It's very straightforward. Only firm one, only the efficient firm will be active, and C2 is what we call a limit price. In formal terms, if firm one maximizes its profit is just this here, okay? Price per unit price minus per unit cost times output. So this would be the profit minus, so this is a Lagrangian approach. However, it's actually not a Lagrangian, but a Kuhn-Tucker approach. This expression here, the P1 minus C2, which is appended with Lagrange multiplier lambda, which is actually a Kuhn-Tucker multiplier, and the whole condition is, technically speaking, in a complementary slackness condition. This problem is actually straightforward to solve. What are you doing? You just maximize your profit. And of course, what is profit maximizing? It would be the monopoly price. So you get PM, the monopoly price, given C1. Of course, if your rival has a cost which are lower than this monopoly price, you cannot charge this price because your rival with actually higher cost would undercut you. So if the monopoly price is above the rival's cost C2, you set this so-called limit price P1 equal to C2. And in this Kuhn-Tucker approach, this complementary slackness condition just accounts for that in technical terms. If your monopoly price, given your low cost level C1, is below the price of the rival, you will charge the monopoly price. Okay, is that clear? Okay, so the point is here, what we assume in particular here with respect to P1 equal to C2, typically we would say, okay, you get the whole market only if you charge slightly less than your rival, so maybe C2 minus some epsilon, minus some small value. We just assume here the following tiebreaker rule, namely that X2 is 0 if they charge the same price. What does it mean? If you have lower costs than your rival and you charge a price equal to the rival's cost, we just assume, and this is what is called a tiebreaker rule, that the rival then produces nothing. Okay? The rival is indifferent between any production quantity when making 0 profits, and we just want to save on notation here. Otherwise, we would also always have to write P1 is C2 minus some epsilon, but this is just tedious. Okay, that's what we are not doing here. Is that clear so far? Hopefully, yeah. We will do that in the. I think I could also put the assignment here as well. I think this might be in the second assignment anyway, but we will very often use and look into that. The second workhorse model we use here is the so-called Kuno oligopoly, named after Auguste Kuno, another French economist or mathematician who developed his model some 50 years earlier than Valdra. And again, the simplest case is a duopoly, again with homogeneous products and a standard inverse demand function. Here, price, and again, price is here a function of aggregate output. Aggregate output is just output firm 1 of firm 1 plus output of firm 2. Again, negatively inclined demand curve. And the important point is here that in Bertrand, firms choose the price, and we end up with this Bertrand paradox with homogeneous products and all the other assumptions I explained a minute ago satisfied. In Kuno, it's completely different, as you will see in a second. Firms maximize profit. If firms maximize profit by choosing their, if it's firm 1, it chooses X1 by choosing its output. So output is a strategic variable. We get a completely different result. Okay, that's what you will see here. Unfortunately, I made it too big, but anyway. Okay. So same kind of profit notation and function. Okay, x1 times the per unit profit p minus c. But if we take a derivative with respect to x, we get the first order conditions, which look very much like the monopolist first order conditions. The only difference here, again here, this expression is marginal revenue. The only difference is here from the monopoly position that this is only the output of firm 1, and in a monopoly case, of course, it would be the market output. And the price depends on market output and not on the output of firm 1. Okay, the same holds for firm 2. And what we have as a result, which is very interesting, and you will see that later in more detail. First of all, price is above marginal cost, because here this expression, this term here is negative. Putting the C and this negative term on the other side, you see that the price is marginal cost plus something. So what we get here as well, and why it is that P prime is negative, that the price under Kuno is higher than the marginal cost. Okay, why is that interesting? Because in Bertrand we get a completely different result. Okay, we get price equal marginal cost. Here we get a different result. Okay, that's rather important. And the nice thing about Kuno is that it's the result is in between perfect competition, or lies in between perfect competition and monopoly. And in I/O, I deal with that at some length, showing that as the number of firms increases, for instance, price will approach the competitive limit. And we will discuss in, I don't know, chapter 3, I think it's when we discussed the Skupta-Stiglitz model, we will discuss market entry and so on. We will allow for a larger number of firms. So be sure to be well acquainted with the Kuno model. Hopefully that's clear so far. The learner index here, we already produced that previously. It's again straightforward. We just manipulate here our first order conditions we have here. Again, you would just factor out the P, you get 1 plus something here. That's what is written here. Again, we have the demand function. Just note that here, that's not so nice, that dx dp is nothing else than x prime of p, and of course p prime would be nothing else than dp over dx. Okay, just in case you're not familiar with this notation. The important point here is that all these x here is just the aggregate output, x1 plus x2, okay? And of course, the dx, the change in x, is always 1. And if the output of one firm changes by 1 unit, aggregate output also changes by 1 unit. Yeah, and manipulating the first order condition yields the learner index. We did that, I don't know whether I did it in detail, but here is what you get rearranging that. So the only thing you have to do is just here expand that by x1 plus x2 here and here, x1 plus x2 in the numerator and the denominator. Of course, that's just 1. And so what you have here, using different colors perhaps. What you have here is x1 or xi divided by aggregate output. That's nothing else than alpha I, which I define here as a market share of firm I. Okay? And what you see here, now this is just our definition. This is just our definition here of the elasticity, actually of 1 over the elasticity. Okay, we get a very, now I have to erase it again, we get a very similar result to the monopoly case where it was just, hopefully we had it at all, but here if you have alpha, in monopolist of course, in the monopolist case alpha is equal to 1. And therefore you would have 1 over epsilon. This is the inverse elasticity rule in a sense. And you see that if you have more than one firm, if you have two firms which are symmetric, you would have 1 over 2 epsilon, and therefore the price would be closer to marginal cost. The learning index would be smaller and you would have smaller market power. Oh, that's just a definition. Okay? Hopefully you are still able to follow me here, but this is all pretty much just a reminder or a refresher what you should have done in your undergraduate studies anyway. What you probably or perhaps have not done in that detail, and I just want to briefly mention that product differentiation. Remember that product differentiation is one reason why if firms choose prices as a strategic variable, while price is not equal to marginal cost. Here we have two different kinds of product differentiation, namely vertical and horizontal product differentiation. Vertical product differentiation, I think I don't go into the details here, just means quality differentiation. This, of course, is interesting for economics of innovation as well, because if you're able to increase the quality of your product, it's very important for you how that affects your market position and how consumer demand will change. We will probably get back to that problem later. Here at the moment, we want to discuss horizontal product differentiation. What does it mean? Yeah, you somehow try to distinguish your product from the other firm's products. And there are two approaches, the love of variety approach and the ideal variety approach. The latter is very often related to spatial competition or something like that. In the IO course, I teach or I discuss a lot about the so-called hoteling model. Here it's this is just the example of the bakery. I just produce, if the bakeries are located further apart, you have an ideal variety. Actually, you would want a bakery just next to your house. Okay, that would be your ideal variety, and typically the assumption is given prices are equal, you just visit the bakery which is closer. And therefore, you get some reduction in the intensity of competition if the distance is far between the two varieties. You might also have a love of variety approach. Love of variety approach means you produce or you demand several products. If you think in terms of music or books, or books, or also in terms of restaurants, typically most people would not have an ideal variety, that is always go to a Hessisch-style restaurant and eat grüne Soße, but they would go one time to a pizzeria, the next time to a Greek restaurant, then a Chinese restaurant, and so on. That would be love of variety. And the question is always here, how many variants that's the question from the welfare point of view. How many variants should we have? It's also a question, of course, for a single firm. In IO, I gave you the example of shampoo. The question is, for instance, for Procter & Gamble, whether to churn out a new version of its Head and Shoulders shampoo. Okay, adding an additional variant, that would be an innovation, and how much would be the willingness of consumers for that? Of course, from a social point of view, the question is whether we have too much or too little differentiation in IO course. I give you example by how many shampoo variants we have, and at least men are typically totally lost when faced with 25 different versions of the shampoo. Okay, LAFO variety approach is here in more formal terms, assuming that we have a representative consumer. That means we have all identical consumer and a strictly concave utility function. An example here is this linear quadratic utility function, which goes back to Bowley in the 1920s. I will explain it in a minute on the next slide. And we have typically some homogeneous numeraire good. We often look, if you, for instance, take the international trade course by Jürgen Meckel, actually what you will very often have a Cobb-Douglas upper tier utility function, and that's what we have next here, a CES utility function. This is what is called a CES utility function. We will, of course, we will get back to that once we talk about adoption and diffusion, and I will explain it then in more details. The point is that such a function gives rise on the individual level to a demand function, which is just the same as the one we have here. The only difference is if we have several products, we would have some measure of all other companies' prices. Okay, there would be some price index. This has some exponent here, and that's what this kind of utility function yields so-called isoelastic demand curves with a constant elasticity of demand. Okay. Yeah, we will get back to that later. I don't expect that you understand it right now, and also this Stone-Geary function is not so important at the moment. What is more important here, because I just want to show you that it's not so complicated as it looks in the first instance, by going back to this Edgeworth-Bowley linear quadratic utility function, which also looks terrible. Okay, I have to confess, but it's actually straightforward, even though this expression is really sloppy put. But just if you think in terms of we have just two differentiated products and a numeraire, how would it look now then in this case? You would have U, and I start now just with the Y because it's easier, Y plus the U, and if you have only two products, you would have A1 X1 plus A2 X2, okay, minus 1/2 B1 X1 squared minus 1/2 B2 X2 squared minus gamma X1 X2. That's how it should look like, okay? That's your utility function. This linear quadratic utility function. Yeah, and why? Hopefully you can also read the last part here. What if you want to maximize utility? You are doing that by actually, usually you just start with a Lagrangian approach, but here it's much easier because you see the Y here enters linearly. And you just can substitute the Y here by M minus P1 X1 plus P1 X2. So I just erase that here, and I could now make some experiments which don't work with my I just add here minus P1. Probably I run into trouble again. X1 minus P1, P2, X2 plus M. Okay, now we can directly solve for the optimum or for the utility maximization just by taking the derivative with respect to x1. Of course, when doing the substitution here in the utility function with y, we always have to guarantee that y is non-negative. Okay, but that's if m is high enough, it's always non-negative. That's what we always assume. And so what we get here is a1. If we take the derivative with respect to x1, we get a1 minus 1/2 b1 x1, and we get the 2 down. So that's actually why this 1/2 cancels out. So minus b1 x1, and then we have here the x1 at the gamma, so we get minus gamma x2. And we have here the price minus P1, and somehow I run into trouble right now with my space, but here just to show that this is something like different. And going back here, minus x1, and that's supposed to be equal to 0. But what you see here, what you have got now, oh, I just cheat a little bit. I erase the 0 here. Okay, and I also erase that equality sign. And what I do as well is, what was the blue here? I just write a colon here, which is a very strange colon right now. Colon. Okay, here. It's not a text model. No, now it's supposed to be a column. And now what do you have here, but with the wrong color? Is equal to, the left-hand side is equal to P1. What we have here is nothing else than the inverse demand function. And you see this is a linear one. If gamma is 0, this is a standard linear demand curve. Okay? And if gamma is positive, you see, then you have a closed substitute. And if you get more, if you have a higher x2, you have a lower willingness to pay for P1. And why is that important? If you have if you thinking about producing a new product, you have to have an idea what the willingness of consumers is for that. Okay? We also will have examples where we calculate that, but the point is, or what I try to make clear, and hopefully I somehow managed to do that, that even though this linear quadratic function doesn't look that nice, it gives a really nice demand structure, namely just a standard kind of linear demand function for differentiated products. And of course, for firm 2, I could do the same, and I would get A2 minus B2 X2 minus gamma X1 is equal to P2. Okay? And we will have a problem, but not an assignment 1 on that. And the important thing is, if you come up with a product innovation, a new product, if you think about as Kellogg's to get out a new cereal, you need to know what this substitution parameter gamma is. How much is the willingness to pay? How strong is competition? Okay, or if you have a Seitenbacher new muesli variant or a Procter & Gamble new Head and Shoulders variant, the question is, how much do you get? What is the willingness to pay? And this inverse demand function gives you nothing else than the willingness to pay. Okay, what we need for our analysis, because we are interested a lot in what consumers are doing, is what consumer welfare is. It's how do we measure consumer welfare, and that's as always with consumer surplus. And consumer surplus is just total willingness to pay for a unit minus what you have to actually pay. And if you have a standard demand function here, Q as a function of the price, or the inverse demand function, which is nothing else than the demand curve, you can immediately derive the consumer surplus by using these integrals here. It's much easier if you start here with our standard demand, our standard market diagram. Here you know what is your consumer surplus. This is consumer surplus. And how can you calculate that in formal terms? Of course, here, if you have linear demand, you would just say this is P bar over minus P0 times Q over 2, okay? Because it's just a triangle, so no need to use an integral. But in the assignment 1 here, you see, again, I just give you the assignment. Here, the Q of P minus epsilon, this is a demand structure which more looks like a hyperbola. Okay, there you need, it's no longer a triangle, and therefore if it looks like an hyperbola, your demand function here, so this would be Q raised to the power of minus epsilon in this case. You need to use the integral, and I erase it again, okay? Because here I want to illustrate these integrals, how you come from the diagram to the integrals. Here, this second integral here is very straightforward. It's just the integral below the demand curve, okay? And it's from 0 up to Q P0. And of course, you get then the whole trapezoid here, inclusive of the expenditure you have, P0 times Q of P0. Of course, in order to get the consumer surplus, which is a triangle, you just have to subtract here your expenditure. Another way to calculate it completely analogous is to just integrate in this direction. Okay, in a sense, you integrate then the inverse of the inverse demand function, so the demand function, and you do the integral from P upper bar to B0 and the here demand function, which would be up here, this demand function. Okay, but this is straightforward, and if there are any questions, Max is forced to take them. Okay, yeah, I think this is almost, we are getting to the end here of this part. Here the monopoly, this is a standard diagram for the monopoly. I just don't remember where I had it already. We had it already, I think. Here, constant marginal cost. And of course, the green area is the important one. I think that's what I illustrated already, because this is what you make in terms of producer surplus. Of course, in order to get profits, you have to subtract fixed cost or any product development cost. The bad thing about the monopoly solution is, of course, that you have here this deadweight loss, because the monopolist doesn't want to sell this much unit, because then he would or she would have to sell it as a lower price, and that would mean that this operating profit goes down, and this is then smaller than the green area. So you get an inefficient situation, which is explained in more detail here, unless the monopolist cannot charge different prices from different consumers, that is, cannot price discriminate, you will have this deadweight loss. And of course, the monopolist is only interested in her own profit, not in consumer surplus. And therefore, the monopolist undersupplies relative to the competitive outcome, and we get allocative inefficiency. Oh, that's interesting. Do you remember Schumpeter? Do you remember creative destruction? Actually, what he had in mind when he thought, I could jump back to the last part of the, I'd have to do it differently. I could jump back to the last part of the quote I gave you, if I manage to find it here. the last part of this quote was static versus dynamic efficiency. It becomes of comparative indifference whether competition in the ordinary sense functions more or less promptly. So what he had in mind is that this triangle, which is this red triangle, which is a static welfare loss, DWL, doesn't matter if we can be sure that in 2 or 3 or 4 years this company is thrown out of the market because it's Nokia, they charge high prices on their phones, and now Apple comes up, okay, and supplies consumers with a completely new product. Okay, that's why it's important. So this is this question from static versus dynamic efficiency, and it's also important in terms of the optimal patent length. We know on the one hand side, we will only get potential innovators to innovate, to invest in innovation, if they can make profits, okay? If they can make profits, if they have monopoly power, we will have a deadweight loss, okay? So in chapter 5, I think it's on patents, we will have to trade off this, the incentive to innovate, which depends very much on a degree of monopoly power, and the deadweight loss we have, okay? So here there are distributional concerns, of course, in particular if you think of medical drugs. Of course, if medical drugs are invented, you want to have that they are available to everyone and at a price close to the production cost. But the problem is, in the first place, you want to have these medical drugs developed. So here is really an important trade-off. I don't want to discuss that with the monopolist being large. I do that in IO and in regulation. So here you get some references if you have problems. So this is just really a standard kind of intermediate microeconomics we had, and you will find all these topics in all the different books. You don't need to go to such an advanced text as Jean Tirol's Theory of Industrial Organization, even though, of course, that's our Bible. Okay. Yeah. Now I move on to the basic model. Okay. I want to discuss right now a set of questions which we already posed in the very beginning of the course, namely, remember Schumpeter. Remember Schumpeter, where we discussed whether it's necessary to have monopoly power in order to get innovation. So the question, which with economists dealt a lot in the last 70, 80 years, is which market structure provides the right kind of incentives or the best kind of incentives for innovation? Is a monopoly better or more conducive to R&D than competition, or is it the other way around? The next question, of course, is are these incentives the right ones the private investors get from a social point of view? I showed you this table from with the different rates estimates of the rates of return. And what you saw there was that the social returns are typically much higher than the private returns. So we would expect that we have underinvestment in R&D, and we just look into how the market structures, how the different do in terms of providing the right level, right incentives, and therefore leading to the right, in a sense of socially optimal level of innovative activity. And finally, and that's only for say the next lecture, the question, if we have an incumbent producer of something like say a Microsoft with its Windows operating system, and there is some innovation pending, or some small company, some startup comes up with a new idea, and is it Microsoft who will implement this new idea, or will a potential entrant do that. Okay, and here we will see these potential entrant provides a threat of entry, and what we are looking into is how that affects the monopolist's willingness to pay for an innovation, and therefore will a monopoly persist for a long time. We might discuss a topic which is called killer acquisitions right now, but that will be at the end of the next lecture, or even in the next but one lecture. But that's rather abstract for the moment, and I will give more examples then. I want to start with a really famous model, namely the paper by Kenneth Arrow from 1962, Economic Welfare and the Allocation of Resources for Inventions, one of the most cited papers at all. And Kenneth Arrow received, among other things, among his studies for information economics, the Nobel Prize also for this kind of analysis. So what we are doing, we compare now competition, perfect competition, or actually here Bertrand competition, and monopoly, and look how they or which kind of incentives to innovate they provide. In order to do that, we look into a process innovation. What does this mean? There is some new technology discovered which reduces unit costs from some level K to some lower level K lower bar. Okay, and the question is here, what is the gain from this innovation to a firm that is the only one to undertake R&D? So what is the gain from innovation means how does the operating profit increase if you introduce this cost reduction, for instance? And the assumption here on the only one to undertake R&D, here, just assume we are thinking about Daimler, and one of Daimler's employees, some engineer, has an idea how Daimler could reduce its production costs. Then, of course, it's clear either Daimler implements this innovation or no one else can, because the engineer is forced to not disclose any important information. Okay. So this would be the case. Later on, we will assume, and this is, however, in the part on the threat of entry, that an independent laboratory or came up with a new process, and it runs an auction, and where both a potential entrant and an incumbent can undertake that. But this is not the assumption here, and it should be clear in a minute. So we get two cases. We have the monopoly and Bertrand competition, which, of course, as you learned above, leads to price equal margin and cost, and therefore is pretty similar to a perfect competition. And we define here drastic and minor or gradual innovations. What is a drastic or large or major innovation? A drastic or major innovation is one where, given you have now the lower costs, K lower bar, the monopoly price you would charge with this lower cost are below the cost of your rival, or below, if you're the monopolist, below your previous cost. Okay? Remember up there when we discussed asymmetric Bertrand duopoly. If you are limited or bound or restricted by the costs which previously were, it's only a gradual innovation or non-drastic innovation, because you cannot set the monopoly price given the new cost, but you're limited to charge a price equal to the rival's marginal cost in case of competition. Okay? Now, just in the notes, I gave you some examples about process innovations, how that might look like. I also give you the source. What is interesting is CNC, computer numerically controlled machine tools, are rather interesting innovation, or have been an interesting innovation in for machine tool makers and for the manufacturing industry. And here's an example of a precision ring maker who produced thin gauge or gauge shims. What are thin gauge shims? I had to look that up. These are, I almost forget it, Messscheiben. Okay, now they produced it for the aircraft industry, and what is really interesting, with conventional technology, these Messscheiben cost about £4,000 to produce. But with the new technique, the cost was about 30 pounds, so less than, is it 100? And of course, this is really a drastic innovation. Okay, and there are other examples here as well. So getting back to our formal analysis, we are now looking into the case how our model works, how or what the willingness to pay, what the gain from innovation is under monopoly and under competition from introducing a process innovation. And I want to start with a graphical analysis, and you will see how wonderfully I animated this diagram. So here, as always, we start with two axes, the one denoting the quantity, the other denoting the price, and we start with a demand curve. Add the marginal revenue curve at double the slope, add the original marginal cost, and of course, what we note that we are talking about the monopolist incentive right now. I should use a red, it's probably better. The monopolist incentive right now here. Of course, the monopolist maximizes profits by setting marginal revenue equal marginal cost. We get then the optimal, the monopoly quantity, go up to the demand curve and to the price axis and get the monopoly price. And what we have here, this yellow area, is the profit the monopolist makes before or with the old technology. Okay, that's a profit with the old technology. And now our analysis actually only starts. Now we look into how does profit change, how does the monopolist profit change if she were to introduce this innovation. And of course, why is that so important to check that up front? You have to know by how much your profit changes if you introduce an innovation, because if you incur costs and it turns out that the increase in cost is higher than your gains in profit, you made a bad deal. Okay, so here now our costs decrease by this amount, okay, and we get a new optimal quantity, and we get a new optimal price, and we get a new producer surplus. Okay, is this new producer surplus, this new profit, the willingness to pay for the innovation? No, it is not, because we gain something, this new profit, but we lose something. This is the old profit. Okay, we use this yellow area, and our willingness to pay is just the difference between the blue area and the yellow area, which is the green areas minus the now red areas. Okay, so this is the gain from innovation for the monopolist. Okay, and the monopolist would introduce or invest in any process innovation, in any reduction of cost, if the costs for introducing this innovation is lower than the green area minus the red area, because then it would lead to an increase in profit. One point I want to mention here, what about consumers? Actually, if it's introduced this better process, the consumers will gain consumer surplus here. Okay, the red area plus this triangle. Okay, so first of all, we learn monopolists have an incentive to innovate. Okay, and second, consumers would gain. There is a consumer surplus, and the monopolists cannot appropriate all these consumer surplus. You will see that that's one of the reasons why we get underinvestment here. Okay. Yeah, then we move on to competition, to bourgeois competition, where only one of the two firms innovates. Okay, so what is the situation to begin with? Now, if both firms have the same marginal cost K, of course, this will be equal to the price. That's clear. So PBK is equal to that price. If one of the two firms introduces this innovation with the lower marginal cost K lower bar, of course, what will be the new price? And that's interesting. The new price will be just the old price. As you see very easily, I could just sketch here the marginal revenue curve. So here the monopoly price would be up here. What you see, it's a non-drastic innovation. Okay, it's a non-drastic innovation because the monopoly price with the new PM of K lower bar is much above the rival's marginal cost. Okay, so that's what you have here. Now you can probably see that, so I don't erase it. Now you see this is now what is called limit pricing. The firm wouldn't change the price. So consumers, that's very interesting. Consumers do not gain anything here from this innovation, but the firm, the innovating firm, makes a profit. Okay, and so the quantity is unchanged, and this yellow rectangle is just the gain in profits. So if the costs of the innovation are less than this rectangle, the firm will invest in this project. Okay. Of course, would it be possible under Bertrand that both firms invest if the investment is costly? No, because no one, if one firm invested, the other firm does not have an incentive to invest, because if it just can catch up, the price would be equal to both firms' marginal cost, the profits would be zero, and they would have losses in terms of the product development costs. Okay, that's what we get. Okay, now the question was, where do we have a higher incentive to innovate? Is it under monopoly or is it under Bertrand competition? And now it should be rather clear. I now just combine these two diagrams we had. Here the gain, the willingness to pay of the firm under competition. Here these two green areas minus the red area under monopoly. And you see the one green area just is already here. We have the same as under, or we have it in both cases. So the only thing which matters is whether these two red areas are larger than the green area, and that's obvious. So the incentive to innovate is greater than the competition. So first result, and in a sense, an anti-Schumpeter result. So here, and that's what I told you in terms of the Spalber quotation I gave you on Tuesday, is that in the setup of Arrow, competition leads to higher incentive to innovate. Okay. So. And for those of you who don't like diagrams so much, and so much as I do, I also provide a formal analysis for the simple case of a linear demand function. Here the linear demand function is particularly simple. So linear is always linear, but here we assume that we have S consumers, and each of these S consumers has a demand of A minus P. So Q is just S, the number of consumers, times A minus P. This would give us a inverse demand function, that is a demand curve of A minus, hopefully I'm correct, Q over S. Okay? So if you still are able to follow me, this is now just the formal analysis, where we just look or formally calculate the incentive to innovate under monopoly and under Bertrand competition. Actually, I think it's assignment 2, where you will have the chance to calculate all these things as well. Okay, linear demand. The monopolist's profit as a function of marginal cost K is just written here in this so-called reduced profit function. Hopefully, I don't know whether it's obvious for you. That's why I thought I just calculated, and therefore I use, if I find it, yes, here, the notebook, and the OneNote notebook is actually our Kursnotizbuch, so the notepad or notebook of the course, and you will find these notes also then in you can look it up in your OneNote notebook. And of course, I have to change to this part now also in OBS. So what we had here was pi. Oops, if it works, I rather use. We have pi, and we had a demand function, which I unfortunately forgot, but the demand function or the demand curve, the inverse demand function, P was A minus Q over S. And then we just write here A minus Q over S times Q minus what was our Q was our, I think, was our marginal cost times Q. And now if we take the derivative d pi dq, it doesn't work so well at the moment here, we simply get A minus 2Q over S minus K, hopefully I do it correctly, is equal to 0. And what we get then here is that Q is equal to, am I correct here, hopefully? Did I make a mistake? I multiplied this here? Yes, should be. The problem is I cannot read my own handwriting because this was not a Q, but it was an A. That's how I got up with the mistake here. So then Q would be, putting the Q on the other side, it would be A minus K divided by 2 times S. Is that correct, hopefully? And the point is, what, and of course then P would be A minus, I have to look it up here, unfortunately, A minus K times S over 2 divided by S, so that we get rid of the S, and actually we get the well-known result that the price is equal to minus 1/2 here, the minus A plus K over 2. This is just the vertical intercept is A plus marginal cost over 2. This is a standard thing we get for price. Now, how do we get our reduced profit function we had previously? We just substitute here the P and in particular the Q into this profit function, and our result will be this expression here. Okay? And this is a so-called reduced profit function, which gives you already profits directly as a function of marginal costs. Just taking into account that the price will be just A plus K over 2, and the quantity will also be something. So once we get that, hopefully it's has been clear. Once we get that, we can calculate the gain from innovation. And the monopolist gain from innovation, and the gain from innovation is just new profit, so profit with the new, with the process innovation introduced with the lower cost, minus a profit with the old technology. And this is delta pi. And now for the monopolist, we just, I make too many lines here. The monopolist is just this expression. You just substitute K and K lower bar and you get this expression. For competition, it's particularly simple because this expression here is just the Q. Okay, this is just a rectangle. And this is this K minus K lower bar is just the change in costs, which is just the length of the of this rectangle under Bertrand. Okay? And so, first of all, I raise it again because you might not see it so well. What do we learn? The first learning here is that the gain from innovation increases in market size. Larger market implies that you have a higher incentive to innovate, that you have a higher gain from innovation. If you're a larger firm, you have a higher gain from innovation. That's rather important, okay? And that holds both for the monopolist and the firm under competition. And also the second point, also a larger innovation, meaning that this cost change, the lower K lower bar, that is the larger the difference between the original cost and the new cost, is the higher is your incentive to innovate. Okay? So this is your gain from drastic innovation. Of course, this is a one-shot or a static game. If you have, and that's what we will do once we look into patents, if you have a profit stream over more years, you just calculate the differentiated. Oh, someone asked I should put up the equation once again. Actually, if you open your OneNote notebook and the course notebook, which you see here, it's the Economics of Innovation notebook in the lectures part, it should be visible to you. Okay, so you should, if you synchronize that, it should work. Okay, you would be able to see that, and that's a nice thing about using this OneNote notebooks, hopefully. And yeah, so yeah, we will do that, so this will be a part in the tutorial class, not of next week, but 1 week anyway. Okay, so now I discussed that, and of course now we have to compare. We did this comparatively previously, but we also want to give something like a formal proof here, and in order to prove. So what you just saw is here, you just compare these two expressions here, delta pi m and delta pi b, and what we want to show, because we derived this result previously, is that delta pi b is larger than delta pi m, and I just jump again here. If you do that, you just factor out the S, you factor out the K minus K lower bar, and you compare the remaining parts, and you manipulate that a little bit, do it at home, and you see it turns out that this holds if A is larger than 2K minus K lower bar plus K over 2. But the point is, actually, we can prove that by just taking into account that A is greater than 2K minus K lower bar, and that's actually what we just derived in OneNote, okay? Because you saw that in OneNote, just jump back again. In OneNote, you saw that the price is just A plus K over 2. And K, of course, here, if this is, if that's what's written here, and if we jump back here, if your cost is K lower bar, the price is just A plus K over 2, and K is the rival's cost. So what you know that for non-drastic, or this is the proof that for non-drastic innovation, this condition is satisfied. But if this condition is satisfied, we might just write down that what we know is that A is greater than 2K minus K lower bar, okay? But this is certainly greater than 2K minus K, or oh, no, that's not greater. This is equal, I just put it differently, minus K lower bar plus K lower bar divided by 2, okay? But this is greater than, because this is exactly the same here, I just put it apart. But this is greater than this expression because I subtract something smaller here. K, as K is larger than K lower bar, it's clear that this holds. And this is a formal proof for why the incentive to innovate, why the gain from innovation is larger under Bertrand competition. In the exam we won't, and in the assignments we won't expect from you that you provide this kind of formal proofs. What you just do, we will give you specific values for the variables. A is 100 or something like that, and you calculate that. Okay? You have to calculate that. And you will see that in, I think it's assignment 2 or 3, it's rather straightforward, hopefully. And so summing up again, the incentive to innovate is greater under Bertrand competition than under monopoly. And this is also true for a drastic innovation. There it's even simpler because under drastic innovation, both firm under Bertrand competition and the monopolist earn the monopoly profit afterwards for a drastic innovation, but the monopolist, the Bertrand firm doesn't lose anything because it had profits of 0 to begin with, whereas the firm under the monopolist made some profit previously. Okay, and this is already explains to you the important effect which is on work here. Why do firms under competition have a higher incentive to innovate? Because they do not have a replacement effect. Short-Tirol called this the replacement effect. This is a monopolist disincentive created by his pre-invention monopoly profits. This sounds rather complicated, but it's actually what one could also call, and I like this more, cannibalization. So who is the most important competitor of Apple's, oh God, what's the next generation, iPhone 12 or something like that? It's the Apple iPhone 10, okay? The point is, if they introduce the Apple iPhone 12, they will have to replace the Apple iPhone 10, and they earn a lot of profits with the Apple iPhone 10. So this is this cannibalization. And that's what's really important, and that's what keeps them to churn out very often new innovations. Okay, in particular, it's their incentive to innovate is different from a firm under perfect competition. Of course, I abstracted and simplified here because they face Samsung's competition and so on. But I think for many addicts of Apple, it's the most important part where they should switch to the new version of the Apple. Okay. Now, and this result is rather general, also obtained for much more general demand functions. It all goes back to the point that the monopolist typically has a lower or provides a lower demand in equilibrium than the firm under competition. Now we have this result, and the question is, what about Schumpeter? Okay, is this result a contradiction to Schumpeter? Is competition better? Now, first of all, Schumpeter argued more about small firms, and here this small firm under competition takes over the whole market. The question is, does it have the capacity to do so at all? Okay, if there are capital market imperfections and so on, you might not be able to scale your factory so much. And the second point is that the monopolist we consider here is a legal monopolist. There are other entry barriers here. It doesn't have to fear to be driven out of the market, so why should it invest a lot? Okay, so that's typically what doesn't give rise to creative destruction, and he doesn't have to be afraid of that. And that result changes quite dramatically if we allow for the threat of entry. And finally, what we learned in the very beginning is that Bertrand competition is a very specific form of a competition, a very tough and intense form of competition, giving rise to this Bertrand kind of paradox. And this is rather different from Kuno, because here, once you have a more efficient firm, it takes over the whole market. And that will be different in Kuno competition, and that's what I don't turn to right now, but that's what I turn to in probably on next Thursday. There are still 3 slides to go here, and so I get back to this importance of a different kind of competition later on. First of all, I want to look into what a social planner would have in terms of an incentive to innovate. Okay, the social planner. What would be the social planner's incentive to innovate? Naja, okay, now I can do it faster. Social planner, if there is a project available which would reduce costs from K to K lower bar, of course, the social planner would set price equal to P lower bar, and then, of course, set this quantity as output, socially optimal quantity, and the gain from this innovation would be the rectangle plus the triangle. And you see immediately the rectangle was the gain from innovation under Bertrand, and here it's higher. So what you see immediately if you compare, I just put all our diagrams in this diagram, and you see the monopolist and the Bertrand competitor undervalue innovation compared to the social optimum. The social planner has a higher incentive to innovate, which is than Kuno, than Bertrand, which is equal to this yellow triangle, and of course it has a much higher incentive to innovate than the monopolist, because the monopolist has a lower incentive to innovate than the Bertrand competitor. So what you see here is that both market structures provide from a social point of view, insufficient incentives to innovate. We get what we previously already said, underinvestment in R&D, because the incentive to invest in something is lower than the social gain. And why is that? Because, of course, a firm cannot appropriate all consumer surplus. Okay? So what does this mean? What is the consequence of this welfare result? Naja, suppose the costs, I just jump back here, the costs of the new research project would be larger than this rectangle, but smaller than the rectangle plus the triangle. Then the social planner would introduce or implement or invest in this innovation, but the firm under Bertrand would not. Okay, so in that sense, you could get insufficient investments. Yeah, so this would be an argument, or this is an argument often put forward for R&D subsidies, because you cannot appropriate all consumer surplus. What is interesting here, of course, firms would always like to have subsidies, even in cases where the profit gain is higher than the investment costs. This would be a mid-norm effect, the lack of additionality, so you always have to check for that. Just one final point here. What about consumers? Strange thing is that with the monopoly, consumers gain from the introduction of this innovation, because prices went down from PMK to PMK lower bar, whereas in Bertrand they don't gain because prices stay at K. Okay, and what does it mean is then, nevertheless, for consumers, is that worse to have competition? No, that doesn't hold, because you remember that unless it's a drastic innovation, the monopoly price will always be higher than K, and under competition, the price, under Bertrand competition, the price is K. And if you have a drastic innovation, of course, the prices would be the same under competition as under monopoly, because there is no more competition. But the point is that given that the monopolist has a lower gain from innovation, it's less likely that the monopolist would introduce this innovation. Okay, this is the consumer surplus effect, which I already told you, that firms cannot appropriate all returns from R&D. Actually, that's where I wanted to start. To stop. This is pretty much it for today. I think we can discuss a little bit longer on WebEx about some further details. But for the moment, that's what I wanted to tell you. I thank you for joining me for this second lecture. I want to say goodbye and see you in WebEx. Thanks.